All right, math and beats, and we're here to start another journey. This time we're going to be diving into the topics of infinite sequences and more thoroughly infinite series. But we got to start with infinite sequences. So here is your introduction to infinite sequences, and let's get going here. Okay. So first, we're going to just consider the set of all the natural numbers. This set right here, that is the collection of counting numbers, 1, 2, 3, 4, and so on. So we've seen these numbers before, and of course, they go on forever. Now, this is actually an example of our first topic, which is called an infinite sequence, right down here. So you say, well, okay, that's great. Got this whole collection of all the counting numbers, 1, 2, 3, 4, 5, 6, and so on and so on. And that's supposedly an infinite sequence. So what is an infinite sequence? Well, that is, it's a set, just like we have with the set of natural numbers above. And in general, an infinite sequence is a set of an ordered list of numbers, and it continues indefinitely on and on and on. So it's ordered, starts somewhere, then it goes on in some pattern in some way, and it just keeps going in that pattern forever after. That's what an infinite sequence is in general. And we have several different ways of writing such sets, such infinite sets, different notations that we have here. One, consider the way of writing an infinite sequence as follows. This thing I'm boxing in down here. So it's this collection A1, A2, A3, A4, A5, boom, 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 just keep going. That is just listing out the things in the set one by one and keeping track of them. We'll have a little bit more formal definitions of these names inside the set, A1, A2, and 3, and so on, below in a little bit. The other way we could denote a set is, well, just take the stuff in the set, say anything in there, ace of k's, and let it start from k is 1 and go to infinity. Imagine if k was 1, you'd have A1. Imagine if k was 2, you'd have A2. And you just list them out, boom, 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 over and over and over again, forever and ever. These two things really mean the same thing. So in number 2, it's more of a condensed version of writing what you see in number 1. It's still listing them all out, but it's saying maybe we have some way of expressing any general term in the sequence in some way, and in that way we express it through k, as we're going to call it the index k, and you just let it go on and on and on. So it means the same thing. Or if you're being real lazy, just write it without those little symbols on the right, just the sets of ace of k's. It means really the same thing. And the advantage in number 3 versus number 2 is that usually in number 3, we just assume k goes to 1 to infinity. Whereas in number 2, even though we wrote it starting at k is 1 and going to infinity, the advantage there is maybe it doesn't start at k is 1. Maybe it starts at k is 3. Maybe it starts at k is 4. And that's really the difference between you want to use number 2 versus number 3. Now, when we write all these things out, as you may be wondering, we have names for these things. So each of the things, the ace of i's, those are called terms. So we're going to refer to each piece in the puzzle as a term. You know, for instance, if I is 1, then we get A1. If I is 2, then we get A2, and so on. So any general term, when I is something, we get some ace of I in the sequence, and each of those ace of i's we call a term of the sequence. In our natural numbers example we saw earlier, Remember, 1, 2, 3, 4, and so on. In that case, A1 would be 1, A2 would be 2, A3 would be 3, and so on. So first term A1, second term A2, third term A3, and so on and so on. The i's in that notation, those subscripts that we see in each of the a sub i's, call that the index for each term. So for instance, when A1 is 1 in the natural numbers, the index is 1, I is 1. Or when A2 is 2, the index was 2, I was 2. Or when A3 was 3, the index was 3, I is 3. So obviously we're not going to have every single sequence just go 1, 2, 3, and so on. They're going to be fancy patterns and whatnot. But we got to keep track of the terms. So we keep track of the terms. We're saying this is the first term, this is the second term, and so on. That's your A1s, your A2s, and so on. And then the subscript itself, 1, 2, 3, whatever, that corresponds to which term you're referring to in the sequence. And then, moreover, just a little side note here, that dot, 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 like we've been saying, in case you didn't know, we refer to that as the ellipsis symbol. That just means that whatever pattern you're dealing with, it's just going to continue on in that fashion indefinitely. So dot, 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 not just dot, dot, dot. 3 dots and continues on in that fashion. We're going to look at an example here so that we can get a better grasp and how we deal with these infinite sequences. Now you may be wondering, who cares about infinite sequences? Well, they're patterns. We're going to look at so many patterns. And patterns are all part of life. If you could somehow identify the pattern and know what's coming next, then that's great. But even more better, what if you added up all those things in the pattern? That's what we really want to get up. Add up all this stuff, but we're not quite there yet, just to give you some context. So we're going to look at this example here. This sequence, not too crazy. Here we got this sequence, 3, 6, 9, 12, dot, 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 ellipses forever and ever. So you would expect the next one to be 15, then 18, then 21, dot, 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 of course. And you say, okay, I can easily recognize that pattern, hopefully. But how do you express this? Well, there's a couple ways of thinking about it. Notice, first of all, that each term in the sequence is 3 more than the previous term. That is, start at A1. A1 here is 3. That's the first term. Then notice that A2, which is 6, is the same as taking 3 plus that previous term A1. In this case, 3 plus 3 is 6. Also notice that the third term, which is 9, is the same as saying take the second term 6 and add another 3 to it. You get 9. How about the fourth term? Well, the fourth term, you take the third term and add another 3 to that. The third term was 9. Add 3, you get 12. Oh, look at that. We're looking at a pattern here. And we should suspect that in general, any term that you get should be the previous term, and then add 3 to that. So that's what this statement says right here. The next term, a sub k plus 1, is take the previous term, a sub k, and add 3 to that, starting when k is 1. Assuming also that we understand, we know A1 is 3, because you got to start somewhere. So it seems that fits the pattern. Is there another way? Yes. We could also try to figure out what the general formula for the term is. So if k is 5 million, what's the value? If we could figure out a way of finding a formula for that, then we could find a formula for any of the terms. That's what we're going to try to look for. So note that when k is 1, we have that the first term, A1, is 3, of course. It's given in the sequence. And that's just the same as 3 times 1. If k is 2, then notice the second term, which is 6, which we know, is the same as 3 times 2. Interesting. What about when k is 3? If k is 3, then the third term, a3, is 9. We know that. That's the same as 3 times 3. One more. How about when k is 4? The fourth term, a4, is 12, which is 3 times 4. Seems like we're picking up a pattern here. You might suspect that in general, we pick any k, say k is n. Then that nth term of the sequence is 3 times that number n. This allows us to write that any term in the sequence starting when k is 1, that term a sub k is just 3 times the index k. We're going to call that function of k, but in this case, please take note, this is really not a continuous function. It's only true when k is 1, k is 2, k is 3, and so on. For this reason, we often refer to this as either a sequential function or a discretely defined function. It's not continuously defined, but it's still a function, and we found a pattern. So these two different ways of expressing the general term in the sequence are two main ways that we want to look for, if possible. Not always possible. What are those two ways? Well, we call one of them, the first one we looked at, the recurrence relation, or sometimes referred to as the recursive formula, where each term is defined by the previous term, or maybe more than the previous term, maybe previous terms. So like a couple of them, 3 of them, so on. But in general, the smallest of the situations is when you can find the next term, a sub k plus 1, from the previous term. So really that next term depends on the previous term, hence that next term is a function of the previous term. Again, defined sequentially, and in this case, at least a1 is given. If it depends on more than just the previous term, you're going to have to know more than just the previous term's value. You're going to have to know maybe more than 1, 2, 3, whatever, depending on how complicated the recurrence relation is. Now, we saw that in our previous example because we saw, let's go back up real quick, we saw that in general, right up here, the next term was the previous term plus 3. That is a recurrence relation for that previous problem. So we did it, now we have a name for it. What's the other one? You know that we did a second way of figuring out how to describe that sequence in the previous problem. And that second way of describing it is, as we refer to, explicit formula. And this is where we say, hey, guess what? No matter what k I have, I can tell you what it is. That kth term is a function of k itself. K is 7. K is 2,300. K is 1 billion. As long as k is a counting number starting at 1 in general, then guess what? We should be able to say what that kth term is, that a sub k, and that's when we refer to the way of defining it or describing it as an explicit formula. Again, it's a sequential formula, not a continuous formula because of k is 1, 2, 3, and so on. In the previous problem, we found that the explicit formula here was 3 times k, if you recall. That was your explicit formula for that sequence itself. Because we found that any term, the kth term, a sub k, is just take that k and multiply it by 3. I can tell you what it is. So these are our two main ways of describing infinite sequences. And we also described in this video what infinite sequences are. We are interested in going further with these sequences. How do they behave? Depending on what's going on, can we say something about what comes next? And then eventually, given that we have some understanding about infinite sequences, can we then take the terms in a sequence, add them up, and then say things about those? Kind of an abstract concept, but it's really important in the grand scheme of math and science. So that's your intro to sequences. Next comes more in-depth dissection of sequences. So stay tuned for the next video and you'll see those things. Okay then, bye now.